All right. Well, uh, hi Luigi. How are you doing
Hi,
today?
I'm fine.
So,
As fine as
uh,
I can be.
really, is everything okay?
Yeah, yeah, it's fine.
Okay. Nothing that you want to share with the whole world, I guess.
Yeah.
Right. All uh, six of the people who might watch this video. But anyways, so um, right. So this in this discussion, I'm going to tell you about my idea of how to construct states of quantum geometry specifically in the framework of loop quantum gravity. Um, and these states um, are the quantum geometric equivalent of the wormhole states which have been constructed by Maldacena and Susskind and studied by many people over the past several years. Right? All of these papers, which are based on wormholes on in ADS, they all work with many of them or most of them work with ADS2, right? So ADS2 is just it has two boundaries,
Hmm.
right? If you have ADS3, there would be a time-like boundary, which is one boundary,
Hmm.
right? There would be a spatial section and a time-like direction. But ADS2, the spatial sections are just lines. Um, and unless you make the spatial section periodic, but then there would be no boundary at all. No, so that the spatial section goes off to infinity on either side, and you basically have 2 points. And so when you trace that over time, right, you get two boundaries, one on the left, one on the right.
Hmm.
So so what happens is that um, um, in that case, you have two Hilbert spaces. You have a Hilbert space living on the left-hand side and on the right-hand side,
Okay.
right? And so you can construct states which are entangled states between the two Hilbert spaces.
Hmm.
Right? And so this was first, to the best of my knowledge, constructed by Maldacena back in 2003. And now you can study a particular kind of state which is called a thermophile double.
Mm.
Again, the details of the thermophile double are not important. I'm just trying to give the historical context of the work.
Okay.
So the thermophile double, uh, as the word suggests, it represents a thermal many-body state,
Mm.
right? So you can assign it has a temperature and everything associated with it. And but it's a pure state. It's not a thermal state. If you trace over any one of the Hilbert spaces, let's say the right one or the left one, the remaining state is a thermal state in the Hilbert space you have not traced over. So it's a way of taking mixed thermal states in one Hilbert space and mapping them to pure states in a doubled Hilbert space, basically,
Hmm.
right? In the language of quantum information, this would be called purification. I think so.
Okay.
So now, and then what people have argued and shown later is that this state corresponds to a wormhole, which connects the geometry on the left-hand side to the right-hand side. Because in this ADS2, they also put a black hole. And that
Mm.
black hole divides the left and right into two portions.
Hmm.
And so if you draw a line through the center and it crosses where that black hole pinches, the geometry of that line corresponds to it's a wormhole.
Mm-hmm.
So and this construction has been central to all of these works, which have become very famous lately by Jeffrey Pennington, Almeri, Netta Engelhardt, Henry Maxfield, and many others. I mean, I can't remember everybody's name right off the top of my head. Right? You must have heard about it, right? The Hawking paradox solved and all that.
Mm. Yeah.
So that is what this is based on. So what I do in my construction, in my wormhole construction, basically, is that I have two copies of a Hilbert space. Each copy, so the Hilbert space represents a three-dimensional geometry.
Mm-hmm.
So having two copies, I can construct states between the two, which are entangled states. I can construct thermophile doubles, right?
Right.
And then the argument is that this state represents a wormhole connecting two three-dimensional regions.
Mm-hmm.
Well, actually, the geometry, the Hilbert space, is not a three-dimensional geometry, but it's the boundary of a three-dimensional geometry. So it's a two-sphere. So you have two spheres, and then they both have a Hilbert space. Then you can entangle the two, and then the logic should go through, right?
Mm-hmm.
If it goes through in the ADS-CFT case, it should go through here also. And then that would imply that what you have is a wormhole geometry connecting two spatial regions of spacetime.
Mm-hmm.
Right? So this paper that I've mentioned to you just now, is this paper from May of 2022. Coherent states and particle scattering in loop quantum gravity. Right? Now, so what do I do in this paper is I construct this Hilbert space. Okay.
Okay.
Now, actually, technically speaking, this Hilbert space had already been constructed many years back by Ethra Levine and Laurent Friedel. So, but I mean, I believe my contribution is the fact that I show how it is related to particle scattering. That's the one thing.
Mm.
And then the second thing, the more important thing is that using that Hilbert space, you can construct these wormhole geometries. And so if we can do that, then we can establish a concrete theoretical connection between loop quantum gravity and all of these works in ADS-CFT.
Mm-hmm.
Right? It would be a concrete relationship and not something which is airy, just something well, not concrete. I don't know what the opposite of concrete. Okay, so now I just want to explain to you the construction of this of these coherent states.
Mm-hmm.
Okay.
Okay.
So these coherent states, and let me open a different presentation. This one. One second. There are a lot of themes which get connected, and I don't want to mention all of them because then it just sounds like a, like a jumble. So I'm going to stick right now to this coherent state description. Okay, now. Yeah. Second. Okay, yeah. So this is the coherent states and particles standard. So shall I skip all of this preliminaries? If you want, I can talk more about it. For now, I'll skip these preliminaries, right? Because we both agree that there is a need for relating loop quantum gravity to particle physics.
Yes.
So what do I do in this paper, right? What are these coherent states that I construct? Well, they are states of quantum geometry. And in order to understand the construction of these states, unfortunately, you need to know a little bit about this thing, which is called the spinor helicity formalism. Okay. Now it's not difficult to understand. So because if you have any 4 vector, right, you can always write that 4 vector as a 2 by 2 Hermitian matrix by contracting it with the Pauli matrices. Right, the sigmas are the Pauli matrices. So the resulting matrix looks like this. Right, it's 2 by 2, it's Hermitian. And if you take the determinant of this matrix, you can see it. It's the norm. It's p square, right? So this is called the spinorial representation of momenta, right? And this is one of the central ingredients which is used in Penrose's construction of twistor space also. Now, what we are going to be concerned with is our null momenta. And so those corresponding to massless particles. Right? And so for null momenta, p square is 0. So if the determinant of a matrix is 0, right, that tells you the matrix is one rank lower degenerate. And so it can be written it can be written as a product of 2 vectors like this. Lambda alpha and lambda alpha dot.
I'm familiar with that.
Yeah.
I'm familiar with that.
Yeah. Okay. Now what happens is that now we are going to consider the case of the scattering of n massless particles. Okay. And we are going to use this labeling to describe the momenta. And when we do that, what we find is that if you consider the configuration space of the scattering of n massless particles, each point in that configuration space can be labeled by a point in something called a Grassmanian. So I'll tell you what that is in a bit. So we want to consider real momenta, right? People consider complex momenta also. There are uses for that, but right now I don't need that, right? So we just want to work with normal QFT amplitudes. And so for real momenta, there is a relationship between these 2 spinors. One becomes the Hermitian conjugate of the other, complex conjugate, with a plus or minus sign, which depends on whether the momentum is future pointing or past pointing. Yeah. So now that means that for a single null momentum, you need a spinor to specify the momentum completely. Okay.
Mhm.
And for n particles, you need n such spinors,
Mhm.
right? So these are the spinors from lambda 1 to lambda n. And now we are going to take these spinors, right?
Mm.
And we are going to write them, rearrange them a little bit, right? So I'm going to take each spinor and make it a column of this matrix, which is a 2 by n matrix,
Mhm.
2 rows and n columns,
Okay.
right? And so now this matrix you can view as a collection of two n-dimensional vectors, A and B, right? The upper component corresponds to A and the bottom component corresponds to B.
Mhm.
And right, and these are complex numbers, right? In general.
Mhm.
So A and B are complex vectors,
Mhm.
right? Okay. Now imagine that, you can give a description of a scattering process according to any observer, right? So if you have a moving observer moving with respect to
Just a
you,
second. Oi? Você vai até lá com o carro? Putz, eu ia sair com o carro às 2h30. Eu ia sair com uma menina que eu dei match no Tinder.
all right. So we have these two complex n vectors, right? And if we perform a change of coordinates to a different set of coordinates, right, what will happen is that each one of these spinors will transform, right?
Mhm.
Each one of these spinors will, and we can write that Lorentz, if it's a Lorentz transformation, we can write it in terms of an SL2C matrix acting on these spinors,
Yeah.
right? And the same SL2C matrix acts on every spinor, right? Because it's a, not a local Lorentz transformation. It's an
Global.
observer sees the whole state transform, right?
Yeah.
So what that means is that each one of these components of these vectors, right? So AI prime and BI prime are the transformed vectors. And you have this SL2C matrix, which has components alpha, beta, gamma, delta,
Mhm.
right? And so each one of those column vectors transforms according to that same matrix.
Yep.
So alpha I prime can be written as in this way, and beta I prime can be written in this way,
Mhm.
right? And this is true for all the components, I from 1 to n.
Yep.
So what is this telling us? This is telling us that the new kinematic data,
Mhm.
right? The new set of momenta is described by a set of vectors, A prime and B prime,
Mhm.
right? But A prime and B prime are a linear combination of A and B.
Mhm.
Sorry. Yeah, this is stupid. Okay, so you can see from this that each component is a linear combination of the other. So the whole vectors are linear combinations of the other two,
Yep.
right? So what does what does any two, if you have any two vectors, right,
Mhm.
and they're non-collinear, then they span a two-dimensional subspace in your vector
Yeah.
space,
Yes.
right? So if you have AB spans a given slice, a given plane,
Mm-hmm.
And now if you take a linear combination of AB, your new vectors will also lie in the same plane. They can't go out of it,
Mm-hmm.
right? There's a picture after this, I think. No, it's not here. Okay, never mind. But do you understand why this is the case?
Mm-hmm.
If you take a linear combination of any two vectors,
Yeah.
the linear combination will lie in the same plane as those two vectors.
Yes.
That's fine, right?
Mm-hmm.
So that means that you can perform any Lorentz transformation. You can look at it from the perspective of any observer. The kinematic data corresponding to a given scattering event will always lie on this one plane
Yes.
in this n-dimensional complex vector space.
Mm-hmm.
And this object, so you can take any this thing, n-dimensional vector space, and you can consider the set of all k-dimensional subspaces of that n-dimensional vector space.
Yeah. That's the Grassmanian.
So that's a Grassmanian. So, if you have GR1n, for instance, it corresponds to the set of all the lines passing through the origin.
Yes.
GR2n is the set of all the planes passing through the origin. Right? Now, okay, and there are many, many applications of Grassmanians. We see them all over the place. One of the places where they appear is in the calculation of scattering amplitudes. And this is based on this amplitude-hedron formalism, which was developed by Nima Arkani Ahmed and his collaborators over the past 13 years or so. Then there is a relation to error correction also.
Mm-hmm.
But for our case, what we are interested is that these coherent states of quantum geometry are also described by Grassmanians.
Mm-hmm.
Okay, so now we can talk about these coherent states. Actually, it might have been better to start with the coherent states and talk about the Grassmanian later, but anyways. The reason I mentioned the Grassmanian first is because it allows me to connect to the fact that the Grassmanian is a central object in this amplitude-hedron program. So to connect the discussion to the physics of scattering amplitudes. Right. So now, why do we want coherent states? Well, coherent states are classical states, semi-classical states, right? So we want to construct semi-classical geometry. So in order to do so, right, we try to use coherent states. Now, there are many versions of coherent states that people have explored, but there is one particular version which goes by the name of UON coherent states.
Mm-hmm.
UN is the unitary group.
Yes.
N by N unitary group. And these coherent states were first studied by Friedel and Speziale and Friedel and Levine. So Friedel and Levine showed that these UN coherent states, so they constructed these UN coherent states based on the twisted geometry construction studied by Friedel and Speziale.
Mm-hmm.
Okay. So now let's just do a very quick crash course on harmonic oscillator coherent states.
Mm-hmm.
Right? So coherent states, the usual definition is that they are states of minimum uncertainty, right?
Mm-hmm.
That is the measure of classicality of the state, basically. right? So delta x times delta p is always going to be greater than h bar by 2,
Mhm.
right? So what's the best we can do? The best we can do is to saturate that bound. So delta x times delta p should be equal to h bar by 2. That's the best we can do,
Mhm.
right? So, and so these states were studied, I think, by many people. I think Pauli was one of the first people to study them. It turns out that you have this annihilation operator, right? In harmonic oscillator, you have
Mhm.
two operators, right? A and A diagram.
Annihilation and
So you,
creation, yes.
right? Now you can write, and both of these operators can be written as linear combinations of P and Q,
Yes.
P hat and Q hat, right? Basically, it's
Mhm.
a linear transformation from this momentum space, from this phase space to Fock space or
Yes.
something. Yeah, I think you can put it like. So you can write A hat in terms of P hat and Q hat,
Mhm.
and you can write P hat or Q hat, uh, whether you work in, depending on which representation you work in, you can write one as an operator and the other as the derivative.
Mhm.
And so this expression becomes a differential equation which you can solve,
Mhm.
right? So if you work in the position representation, it becomes a differential equation which is d by dq plus q plus iq times psi of alpha is equal to,
Mhm.
and it's an eigenvalue equation. Now, what is this alpha parameter, right? This alpha is a complex number,
Mhm.
and it has a significance. Which is the significance of this is that if you calculate the expectation value of the momentum operators or the position operators in this coherent state, right? So
Mhm.
these expectation values are taken in that coherent state.
Mhm.
Those expectation values correspond to the real and imaginary parts of alpha, respectively,
Mhm.
right? So the real part of, so alpha basically, what does it do now? It labels a point in your phase space, in your classical phase space,
Yes.
right? So in this figure on the right, one axis is a position, the other one should be labeled as with momentum, but
Mhm.
and how do you create these states? You can create these states by starting with your vacuum state and acting on it with this
The displacement.
exponentiated this operator, which is called the displacement operator.
Yeah. Just the
Okay,
basically the explanation of phi times momentum.
exponentiation of,
I times momentum. Because if
no, it's
you
a
when you exponentiate the derivative with respect to x times something,
mhm.
you basically displace the arguments of the
Mm,
function.
mm, exactly. But in this case,
I
we
alpha
want to
times the momentum.
displace in both directions, the momentum direction and also the spatial direction.
Yeah.
So this exponent is a linear combination of momenta, and
Yeah.
so yeah, like you said, yeah, yes, exponential of the, but it contains a position term also in
Mm-hmm.
addition to that momentum term, right? So it displaces, it translates you along the momentum, along the position, and also along the momentum.
Mm-hmm.
And yes, what you just said is very simple and obvious way of understanding what's going on. Now these states are coherent states. They satisfy this condition. They saturate this bound. If you study the time evolution of these coherent states, you will find that the point alpha, it traces out a trajectory in phase space, which is that trajectory is given by the classical equations of motion.
Mhm.
Right? So these are the classical states or semi-classical states.
Mhm.
But this is for a single harmonic oscillator, right?
Yes.
Now, we have many systems in nature, right? So we want to construct some way of, we want to have
Generalizing
some way of
this.
generalizing this to arbitrary systems, right? Like many body
Mhm.
states. So these operators, A and A dagger, right? So now, when we generalize things, we lose connection to the simpler formalism. Things become a little
Mhm.
bit more abstract. So
Yeah.
they generate this Weil-Heisenberg algebra.
Mhm.
And this Weil-Heisenberg algebra, when you exponentiate it, it gives you,
The group.
one second.
Let's continue tomorrow. I have to get ready to go out.
Okay.
Tomorrow
So,
we continue since we are starting
all right.
the next subject.
All right. So far, just to summarize, I've talked about two things. One is this thing, momentum, the spinor formulation of momenta,
Mhm.
and the other is coherent states. And also the Grassmanian symmetry of scattering amplitudes,
Mm.
the spinor momentum relationship, and the construction of harmonic oscillator coherent states.
Mhm.
Okay.
Okay.
And we'll continue tomorrow or in our next session.
Okay. See you